thanks a lot, Aude, and thanks, Freddy, for organizing this week and inviting me. I will, oh, okay, thanks. So this is the first presentation of an ongoing paper with many authors, as you can see. The main author is Hippolyte Sédier, who was intern at CIRED until a few months ago. And among the authors are many people who have either contributed to earlier versions of Eoles or provided worked on the data that we use. So in this paper and presentation, I will both present the Eoles model and this application to the negaWatt scenario. So I will first present the negaWatt scenario briefly, then the model. I will briefly compare this model to other open source energy system optimization models which exist currently. Before presenting the results, just since we are in a school and in which you may be interested in this point on the computational cost of the model, and I will conclude. So the negaWatt scenario, the negaWatt scenarios have been provided by the association of the same name. The first one in 2003, and since then every 5 years. So in 2003, it was probably the first energy scenario in France compatible with a 2-degree target, and so since then it has been complexified in many ways. So the basic philosophy behind this scenario is to rely on 3 pillars, what's the so-called negaWatt trilogy. The first 2 pillars are about reducing energy consumption by 2 ways: energy sufficiency and efficiency. So sufficiency, in French, sobriété, has been introduced by negaWatt, and since then it has since some 2 years it has got a large success, partly thanks to the fact that it has been adopted by in the latest IPCC report. So why this distinction between sufficiency and efficiency? Well, efficiency is energy efficiency is about providing the same level of energy services with less energy. For example, you don't change the number of ton-kilometers that you transport, but you use less energy. And if you reduce the number of ton-kilometers, so this is sufficiency. There are other definitions, but I will stick to this one, which is very simple. So, as Aude has written in a recent paper, I think we can define sufficiency by energy savings, which is not efficiency, if you want. And then you still need some energy, of course, and so the third pillar is to provide this energy through renewable technologies. Here you have many resources to go further, a few in English, most of them in French. So in this scenario is in physical terms. So you have hectares, you have megawatts, you have terawatt hours, and so on, ton kilometers, passenger kilometers. So in physical terms, and so here you have the Sankey diagram of energy in France in the scenario in 2050, just to give you an idea. So you have primary energy on the left, which is renewable in 2050. Then you have many conversions through energy carriers, primary, secondary energy carriers. You have some losses, and then you have the final uses, which are in transportation, heating, feedstock for industry, or specific electricity. of course, I will not present the detail, but just the result. In a nutshell, in terms of primary energy, in 2050, the consumption is reduced by 2/3, and in 2050, you almost only have renewable energy, only a few very tiny part of fossil for feedstock. And nuclear is phased out around 2045. It may appear very, very ambitious, such a decrease in primary energy, and it is, but we have to remind that currently 2/3 of our energy is wasted. So this is for France. This Sankey diagram is provided by the Lawrence Livermore National Laboratory. It's a bit old, it's for 2017. Unfortunately, I don't know any other and more recent. But the interest of this one is that you go from primary energy not only to final energy here, but to useful energy. That is, you also account for the losses in the engines in cars or trucks here, for example. Usually you stop before this step. And then you can see that 2/3 of our energy, more or less, is wasted, mostly in the electricity power plants, but also in the engines, in transportation or elsewhere. And this
Philippe, I have a question regarding nuclear. So negaWatt is not planning to change. I mean, what's the rationale not to adapt to the new plans for France? I mean,
in fact, this scenario was published or developed in 2021. So before the announcement or before a decision was made to build 6 new power plants. So this is not including in the scenario.
But they are planning to update the scenarios?
It's an ongoing debate. I don't know. But usually it's every 5 years. I don't know if there will be one for 2027. And so this is for France, but in the world it's the same. So this is the same kind of data in the world. And we see that when you go from primary energy to useful energy, you lose 2/3 of this primary energy. So yes, it's ambitious, but we have also to keep in mind that a huge part of our energy is wasted. And if we use more efficient ways to produce electricity, if we use more efficient motors, like electric motors, immediately you reduce these energy losses. And this does not even take into account the fact that when you move one person in a car of 1.5 tons, it's also very inefficient. But this is not even taken into account here. This scenario attains climate neutrality, so zero net emissions on the French territory by 2047. And when you take into account imports and exports of goods, so the carbon footprint, it becomes neutral in 2050. We don't model all the scenario here. Only some or most of the energy carriers. Part of these graphs are in French. Electricity, we model electricity, the supply of electricity, hydrogen, and methane. So we don't model the supply of wood, biofuels, and district heating. So this scenario, in the transportation, you have, as I said, sufficiency. So you reduce the number of kilometers of person kilometers. You reduce the number of ton kilometers, and you have some gains in efficiency and also some fuel switch. So for private cars, in 2050, they become mostly electric or plug-in hybrid. And for trucks, mostly they use renewable gas and partly electricity. And for heating, you have a big effort for thermal renovation of buildings. Not all buildings are renovated. Something like 10% are not in 2050, but still most of them are renovated. And concerning, you have also some fuel switch with an increase in the share of heat pumps in gray here. So this is for individual houses, collective dwellings, and tertiary sector. So in gray, you have the heat pumps. But you also have district heating here, some wood in green, and some gas remains, but it becomes renewable. That's it for the negaWatt scenario. Now I will turn to the Eoles model. Eoles means energy optimization for low emission systems, by the way. So it's we have with co-authors worked on several versions of this model. So the first one was just modeling renewable energies. And then we introduced a nuclear power plant, carbon capture and storage, then other energy carriers with a fuel switch in transportation and heating, and then various ways to produce hydrogen. Yeah.
What kind of link do you have between the negaWatt scenario and the models that built it and the Eoles?
I will present it just afterwards. And then some papers were about how to speed up the optimization. And the latest one was a coupling between this model and a model of the energy demand from space heating in France. The principle of the model is very, very simple. We perform a simultaneous optimization of investment in electricity and energy generation capacities and storage capacities, and of the dispatch of these capacities. So we minimize the cost of the energy system, which is sum of the annualized fixed costs and the variable costs under a series of constraints, which are that at every time step, we must generate enough to satisfy the demand and enough energy for the three energy carriers. And also, we cannot produce more than the capacities that we have, and we have another series of less important constraints, including primary and secondary reserves. Then we have many technologies in the model. In yellow, I will try here. Yeah, we have non-dispatchable technologies. Yeah, so wind, PV, run-of-river hydro, combined heat and power, which is assumed not dispatchable because it's driven by the heat needs. We also have some dispatchable technologies in the model, with nuclear and coal that we don't use here because they are not in the scenario. Hydro based on dams and gas turbines. We also have some storage technologies, batteries and pumped hydro storage. We also have biogas, electrolysis. We can import natural gas, but we don't in this scenario. Then we have storage of methane, storage of hydrogen. And on the right, we have the three exogenous demands at a hourly time step: electricity, hydrogen, and methane. And then we have this need for secondary reserves, which is increasing with the level of demand and with the share of wind and PV. So among the main simplifying assumptions, we have a single node, so it's continental France, so we don't model the electricity network inside France, and we don't model the interconnection with the neighboring countries. So the first assumption is satisfying the demand, but the second has the opposite results. We assume that the total demand is inelastic, so we must satisfy completely the demand provided by the scenario, but we will see that we can switch in a limited way this demand for a few hours. It's linear programming because it's much faster. We assume full information, which is something we would like to work on later. We combine variable and fixed cost by assuming a cost of capital by 4% a year. For the wind and hourly capacity factors, we use MERA2 reanalysis. I will develop this in a minute. For hydro, we couple the model with the ORCID, which is a hydrological model of the IPSL, which is forced by another reanalysis, Safran, which is much more adapted for hydro because it's you have a fine resolution for France on the mountains. For the assumption about cost and the energy losses of the various technology, mostly we rely on RTE, future energetic study, with a few exceptions. One exception is for onshore wind. For onshore wind, we use the cost and data from ADEME, which is higher. The assumption about the cost of wind is higher than RTE because the ADEME assumes different technology of wind turbines, which are more costly per megawatt, but produce more by megawatt too. So it's more consistent this way, and it is also the assumption in the, we have the same type of assumption in the negaWatt scenario, hence this exception. Of course, the getting good capacity factor for wind and PV is important. So it's important to check that our data are realistic. So what we use is renewable.ninja system, which has been developed by Fenninger and Staffel. It has been published in several papers. And so they use MERA2 reanalysis from the NASA, and then they apply a bias correction method, which is necessary because reanalyses are highly biased for wind over France. And this provides a very good correlation with the observations of wind generation provided by RTE. You can see here the duration curves, both for PV and for wind for France. In orange, it's observations by RTE. And in black, it's the data that we use, and they are very, very close. Correlation are 0.98 or 0.97. So this paper by Moraes has compared the various such products and concluded that this one is very good. And then for the implementation, we have to assume what kind of wind power wind turbine we use. So it's here, Vestas V110. It was the model the most installed in France the last year. And it's consistent with our assumption in terms of cost and power curve. We use 19 years of hourly data. For the location of offshore wind, we use the projected and existing sites around France. And for the locations for onshore wind and PV, we model one site per département, and we assume that the capacity stay proportional to what they were in 2017. Just they increase proportionally. If we apply this method, then we get capacity factors which are not exactly the same as in the negaWatt scenario. For onshore winds, they are a bit higher at 32% in average over a year. And so to really stick to the scenario as much as we can, we apply a multiplicative factor to get to the same annual average capacity factor. So it's 30% for onshore, 40 and 45 for fixed and floating offshore.
So are these two distributions independent?
No, they are not, because they are based on the same reanalysis.
Okay.
And on this point, we wanted to have a consistency between wind and PV generation, but also with hydro generation and the thermosensitive part of demand. So we use the same time period. For wind and PV, I said it. Hydro, it's not the same analysis, but it's partly the same observation, but there are many more observations behind Safran, because to model hydro, you need to have rainfall in the mountains, and so it's better this way. Now, the heating needs. For the total power consumption for heating, we rely on the negaWatt scenario. Because, of course, this total heating need depends on the assumptions that you have for the dwelling sector and tertiary sector, how many square meters you will have, and how much will they be insulated or not. But then we wanted to spread this overall consumption over the year and over every day. So we relied on demand.ninja, which is a system, it has been published recently. It's also by the team by Staffel. So they also rely on the reanalysis mirror 2. And then, as usual, they assume a linear function relying the demand for heating with the temperature beyond the threshold, which varies by region. And then they also include other factors of heating need, which are wind, for the wind chill effect, humidity, and also the sun to account for passive heating by sunlight, but mostly it's temperature. And so this gives us the hourly profile, both daily and intraday. For the cooling needs, so air conditioning, we also rely on Staffel for the temperature data. But for the daily profile, their equations were not really performing well. So we relied on the sensitivity, cooling sensitivity provided by RTE, which is 700 megawatts per degree beyond the threshold. And for the intraday profile, we also relied on RTE assumptions. But behind, it's always the same weather data set, mirror 2. A few words on the other constraints. So we have two kinds of reserves implemented in the model. Primary reserves, which are really short-term. We take the same amount of contracted power as today. For the secondary reserves, so it's proportional to the, as I said, to demand, electricity demand, and to generation by PV and wind. Also, we allow, I said that the total demand is completely inelastic. It does not change with the price, but we allow the demand to be shifted up to 6 hours, a part of demand. And so this part of demand amount to 7 gigawatt hours per year. It's based on the assumption in RTE, future energetic. It's their, what they call, I think, realistic or pessimistic scenario, I don't remember, but it's the one they use in future energetic. We have also some constraints on CO2 availability, biogenic CO2 availability, to model the power to methane technology. We have some availability constraints for biomass, and for every technology, we have some maximum capacities, which are those provided in the negaWatt scenario. So in fact, what we do is that we cap these maximum capacities, for example, for wind power. So the model can go below this limit. It can install less wind, but it cannot install more. So compared to other open source energy optimization models, what can we say? So Eoles ELEC is the version that we use, which is in the last column here. We don't model heat and transportation. We focus really on the energy sector, so we model the supply of methane, hydrogen. We have different technologies for storage. We don't model interconnections with neighboring countries. We model load shifting. We don't have the internal electricity network inside France, but we model reserves. And so why did we choose this model? Partly because we have it at CIRED, but partly because it allows to model several years at a hourly time step at a reasonable computational cost, which is not the case of the other models open source as far as we know. So the results. I have first to present you the methodology that we use to present the results in various steps. First, we find that the demand cannot be met at every hour during these 19 years. So the model cannot run because we prescribe that it must satisfy demand at every hour. So what did we do? We defined a dummy dispatchable technology, which is extremely costly. And so the model will use it in the last resort only. And then, but then there is no limit, so then the model can run. Just the cost that we obtain is not realistic, but it allows to get some outputs. We find that this dummy dispatchable technology is used in average 3.2 hours per year only over the 8,760 hours of a year. So the negaWatt scenario quasi complies with the failure criterion of the energy code, which is not more than 3 hours per year in average of failure. And this is even without the interconnections. In practice, without the interconnection, today we would have many more hours of failure than 3 hours. Then we ask, yes?
Can you tell us what is the constraint on the supply side that makes demand not met?
Mostly, the amount of technologies, the capacity of the various technology, generation, but also storage, is capped at the levels of the negaWatt scenario. So, and especially the amount of batteries is limited, or every storage technology. So in the first step, we added some pumped hydro storage because there is less PHS in the negaWatt scenario than in RTE, future energetic. So we tried this. It helped, but it was not enough. So we compared for more realistic variants, or at least more realistic than our dummy technology, which meet demand for every hour, even without the interconnections. So the first one is to install more batteries. The second, more hydrogen turbines. Hydrogen being produced by electrolysis. The third, more natural gas turbines. And the last one is the optimal mix, the least costly mix of the three above. So before comparing these variants, just a word about how load shifting is running in the model. So on this graph, on top, you have 2 typical weeks in summer, and below, on the bottom, you have 2 typical weeks in winter. You have 2 lines, one red line and one black line. The red line is electricity consumption before load shifting, and the black one is after load shifting. Remember, load shifting is allowed for 6 hours, but it's limited. And also on this graph, you have the non-dispatchable generation, so PV, wind, run-of-river. You recognize the daily cycle with the peak of PV generation, especially in summer. And you see that every day in these 2 weeks, we produce more around noon than the demand. And so the model shifts a part of demand around noon. But it cannot shift enough, so we still have some curtailment of PV generation. And you also will need some dispatchable power, especially in the evening. So in summer, it's always the same behavior. We switch some load from the morning and from the evening to the midday. In winter, you don't have it's more complicated. Sometimes you have the same behavior when there's a lot of sun, but sometimes you don't shift, you almost don't shift, like on the right here. And sometimes you shift from one day to the other. Well, so for summer, having a very simple incentive for load shifting would be enough, like changing the, just saying people, okay, we will pay less for electricity around noon. But in winter, it's more complex. You would need more other incentives.
And what kind of assumption do you make? Is it you have a number of electric vehicles that are possible to shift, or you just
we just take the assumptions by RTE. So they have a series of consumers which can shift some load, as is the case today for some industries. So with when we run the model with a dummy dispatchable technology, we see that we need around 8 gigawatts of dispatchable power. We have enough energy altogether, but it's when this energy is available. We need for the reserve about 5 gigawatts, so in total 13 gigawatts, which is 30% more than in the negaWatt scenario, if we had every dispatchable technology, the storage or generation. Here I display the week with the largest use of the dummy technology. And this occurs in early February 2006. And you see in gray here the use of the dummy technology in the morning and in the evening, especially because there is very little wind this day. And then we compare these 4 realistic variants to meet the demand, if we want to meet the demand every hour at any cost. So on the left, we see the dispatchable technologies in the scenarios. So you have the dams, you have the PHS, pumped hydro storage, you have the batteries in a very limited quantity in the scenario, and you have some gas turbines, combined cycle gas turbines. And here you see what is missing in gray. So the first variant is to increase methane power plants. And here the model chooses to install open cycle methane power plants, which have a lower capital cost, but a lower efficiency. In the second variant, we install hydrogen turbines. which is basically the same technology. In the third, we use more batteries. And in the fourth, we let the model decide, and the model does not install hydrogen turbines, but it installs both more batteries and more open cycle gas turbines. The costs are very close. So the yearly cost of the system in the optimal mix is around 30 billion euros per year. This does not include the electricity network, just generation, storage capacities, and dispatch. And the other variants add between 3 to 5% costs. The hydrogen one being a bit more costly, but it's very close. Oh, this remote control seems to work after all. Also, we can say that, in fact, in the optimal mix, we can install less PV than forecast in the negawatt scenario. In the scenario, you have 138 gigawatts of PV, but we find that 112 is enough. And doing this, and oh yes, for the reserves, they are satisfied half, roughly speaking, half by batteries and half by pumped hydro. And just removing PV on, especially on roof, some PV on roof, we save 5.5 billion euros per year, which is not small compared to the extra cost of dispatchable technologies. But it's this is only the investment cost, not the overall yearly cost. Just maybe a few words on the time to run the model. So we use the Gurobi solver. And for linear programming, there are several algorithms that can be used. And here we find that the interior point method is much faster for our problem than the simplex. And in fact, on a classical server, we only need 2 to 3 hours to run the 19 years at the hourly time step, which for 19 years at hourly time step, yes, which is not bad given the number of hours that you need to model and that you have storage, and so you have many dynamic technologies here. So to sum up, we find that the negawatt scenario almost ensures the security of supply as defined in the energy code, with 3.2 hours per year instead of 3. We find that PV could be reduced from 138 to 112 gigawatts without problems, and it saves something like 5 billion euros a year. And then we can ask ourselves, is it worth adding 13 gigawatts of dispatchable power to avoid 3 hours per year of failure? In my opinion, well, we have to work more on this and how much it costs and what is the benefit per megawatt hour supplied. I think no, clearly. But clearly, why do I say no? Because in reality, we would have some availability of the interconnections. So some power produced by our neighbors would be available. But to know how much, we need to make assumptions about what our neighbors will do. And this is not part of the negawatt scenario, so we did not want to add this kind of assumption. This is why we didn't model it. But it can be done. So the main limits now. The first limit, of course, is the scenario itself, and especially the final electricity demand, but also hydrogen and methane demand that are in the negawatt scenarios. In the negawatt scenario, are they realistic? On the one hand, I would say yes, because it's really the result of a fine bottom-up modeling in which you have dozens of categories of electric appliances that are modeled. I think it's more detailed than in any other scenario for France. On the other hand, the level of electrification is lower than in some other scenarios, especially in transportation. We have seen that there is most heavy-duty vehicles are powered by gas, not electricity. This may change. This year, the major truck manufacturers are commercializing electric trucks, electric semis. So if the network, if the power charging facilities are there, this could be electrified. So maybe electrification could be higher than in the scenario. This is to be debated. Also, we have seen that it's very difficult to forecast the power consumption from air conditioning. First, because we don't know how many people will install air conditioning in the future due to climate change. And second, because the level of electricity consumption by these air conditioning systems will really depend on the behavior of the people who occupy these dwellings. And this is not a big thing in total energy consumption over the year, but it's big in terms of power available. Well, we don't model inertia, but just reading the future energetic study, we see that you just need to have grid forming capabilities in a part of the wind and PV inverters to maintain frequency stability, so probably it's not a big deal. What is a big deal is that we don't model the electricity transportation and distribution grids, but clearly other models are more adapted to this, like PIPSA or Antares. And I said this already twice, but we don't model the interconnections. And this would allow to install less capacities or to electrify more if we wish. So thank you for your attention. On these links, you have the GitHub with the Eoles model. You have a link describing the various types, all the family of the Eoles model, and the link to the negaWatt site website with many resources in French, not much in English, unfortunately. So thanks for your attention.